A cold front had rolled across Japan's coast like a curtain. The air was a solid wall of fog and rain. Even the harbor lights of Yokosuka were gone, drowned in mist. In a command post overlooking the water, Japanese naval officers studied their scopes. Radar screens flickering with static, weather charts soaked from condensation. No aircraft could fly in this, they told themselves. No bomber formation could cross the Pacific blind. But at 10:12 p.m., the first tremors arrived, a low vibration, distant and growing. Moments later, the spotters heard it, the heavy drone of engines, hundreds of them somewhere above the clouds. The officers rushed outside, straining upward, but the sky was empty. Then, through the storm's endless gray, flashes began, bright, rhythmic, rolling in waves. Bombs. The entire formation had come through the typhoon-level weather without breaking formation or losing aim. No sun, no stars, no radio bearings. Just an invisible pulse guiding them across 1,500 miles of ocean. Hours later, when reports confirmed every squadron had returned, American crews spoke of it as routine, just another night run with Lauren. To the Japanese staff, it felt like sorcery. To history, it marked the moment navigation became electronic. By late 1943, America's air war in the Pacific was reaching the limits of what human navigation could endure. The distances were brutal. 2,000 miles of empty ocean between bases. The weather was unpredictable, radar unreliable, and the stars often hidden by monsoon clouds that stretched horizon to horizon. The result was as dangerous as any enemy gun. Entire bomber squadrons could disappear simply by flying into the wrong front. Crews of B-24 Liberators and B-17 Flying Fortresses learned to dread the oceanic void. Without landmarks, navigation meant calculating position by dead reckoning, measuring time, airspeed, and wind drift. But even a single degree of error could mean hundreds of miles off course. There were no radio beacons out there, no towers, no rescue ships in the black water below. It wasn't enemy fighters that haunted them most. It was being lost. Flight after flight ended with fuel exhausted, bombers ditching into the Pacific, never found. Entire crews simply vanished from rosters. Every mission planner knew the cruel equation. Navigation failure killed more men than combat ever could. The search for a new compass. In Washington, D.C., this problem landed on the desks of the National Defense Research Committee, NDRC, the same wartime scientific council that had built radar, sonar, and the proximity fuse. If radar could find ships, they reasoned, maybe radio waves could locate planes. The concept was elegant in theory and impossible in practice, at least until 1942. A team of engineers at the Massachusetts Institute of Technology's Radiation Laboratory and the U.S. Coast Guard began developing something radical, a long-range navigation system that used the timing of radio pulses to calculate position. They called it LORAN, short for long-range navigation. It worked like this. 2 ground stations, separated by hundreds of miles, emitted synchronized radio pulses. An aircraft receiver picked up both signals and measured the time difference between their arrivals. That difference, often just a few thousandths of a second, represented a line of position on a map, known as a hyperbolic curve. By using 2 pairs of stations, 2 sets of hyperbolic lines intersected, giving an exact fix: day, night, storm, or clear. To put it simply, the bomber no longer needed to see the world. The world told the bomber where it was. Building a web. Across the ocean. Implementing. It was another story. The Pacific wasn't Europe. There were no safe coastlines or cables to link the transmitters. Each station had to be built from scratch, on remote islands barely large enough for an airstrip. The work fell to the U.S. Coast Guard and the newly formed Army Air Force's Weather and Navigation Service. In 1943, small teams of radio men and engineers began landing on forgotten atolls: Attu, Tarawa, Saipan, Biak, Guam, and later Iwo Jima. They brought crates of vacuum tubes, diesel generators, antenna masts, and one rule: secrecy. No Japanese reconnaissance plane could be allowed to see the towers. Each station operated under camouflage netting, transmitting coded pulses so faint that enemy receivers mistook them for background noise. By the end of 1944, the Pacific was crisscrossed by invisible highways of timing signals, chains named A, B, and C. They reached thousands of miles beyond radar range, knitting the Aleutians to the Philippines, the Marshalls to Okinawa. Aircraft flying above the weather could now fix their position to within a mile. It was, in effect, an electronic map drawn on the sky. The first tests. The system's debut came quietly. In September 1944, a B-24 squadron from the 7th Air Force flew a test mission from Guam to Truk, 1,400 miles through shifting storms. Every aircraft made it there and back within minutes of the predicted flight time. No one got lost. The data was so precise that weather officers began using LORAN to chart typhoon drift across the western Pacific. For the first time, technology had defeated distance. LORAN could do what the human eye could not, see through weather, night, and fear itself. It was the bridge between Earth and electronics, between instinct and information. The system would soon move from experiment to weapon. For Japan, this meant the unthinkable. Allied bombers that could strike cities and return home through storms, darkness, and fog, guided by nothing more than invisible pulses from the sea. The empire had spent years believing weather was its ally. In 1945, it discovered that even clouds could be conquered. By early 1945, LORAN was no longer an experiment. It was a full-fledged strategic network quietly pulsing across half the world. The U.S. Navy and the Army Air Forces had expanded it at astonishing speed. What began as a handful of prototype transmitters on fog-drenched islands now formed a continuous chain of synchronized beacons stretching from the Aleutians to Australia, from Hawaii to Luzon. Each chain was made of master and slave stations, precisely timed so their signals never drifted. The intervals between pulses were calibrated to microseconds, the smallest unit measurable by wartime electronics. In the cockpits of B-24 Liberators, the new receivers glowed softly green, their cathode ray tubes showing the world not as geography, but as rhythm. Navigators no longer looked for land or stars. They looked for the intersection of time. At first, older crews distrusted it. They were trained to chart courses by the compass, by the smell of ocean wind, by the memory of islands and currents. But those same men had also buried too many friends lost to the sea. One flight commander put it simply, "If this box can bring us home through rain, we'll believe in it." From island to sky to make that belief possible, the Coast Guard's hidden construction teams worked in parallel with advancing armies. As soon as the Marines secured an island, LORAN engineers arrived behind them, unloading crates, assembling transmitters, stringing antenna cables under camouflage netting, and synchronizing their clocks to atomic precision. The towers rose silently while smoke still hung from the beaches. On Saipan, crews built the network's main Pacific hub under constant artillery echo. On Peleliu, a 625-foot mast went up in record time, hidden under palm fronds and night shifts. Each transmitter sent out a coded pulse every fraction of a second, and, together, those pulses formed what Allied pilots called the heartbeat of the Pacific. By late 1944, the system's reach had grown astonishing. A single bomber over Okinawa could receive signals from 3 or 4 different LORAN chains simultaneously, each crossing line narrowing its position like threads of light converging on a pin. For the first time, pilots could fly entire missions inside clouds and still know exactly where they were. Inside every B-24 fitted for long-range navigation was a small metal cabinet, the LORAN receiver, its screen flickering with bright sine waves. The navigator sat hunched over it, wearing headphones, tracing pencil marks on a transparent chart overlay. 2 pulses appeared on the display, one from the master station, one from the slave. When their peaks aligned, he knew the time difference precisely. He found that value on his hyperbolic chart, drew a line, and waited for a second pair of stations to cross it. Where the lines met, they were. The entire process took less than 30 seconds, faster than a star sighting, more accurate than any compass bearing. Loren turned navigation into mathematics, a discipline immune to fear, fatigue, or cloud cover. It also meant something more profound. Command could now plan operations in all weather. No longer did the Pacific Fleet wait for clear skies or moonlight. The bombers could fly through typhoons, above overcast, and still strike with surgical accuracy, for Japan, that removed one of its oldest defenses: weather. When the enemy noticed, Japanese coastal observers first reported phantom formations in late 1944. They described bombers emerging from storms exactly on course, as if guided by unseen hands. At first, Tokyo's intelligence bureau assumed the Americans had discovered new celestial techniques, perhaps infrared or gyroscopic compasses. It wasn't until 1945, when fragments of captured navigation charts were recovered from downed B-24s near Formosa, that they realized something else was at work. The maps were overlaid not with latitude and longitude, but with curved lines labeled A, B, C, and D. To Japanese analysts, it looked like sorcery. No one could explain what those curves represented. By the time they understood it was timing, the war was nearly over. Japan had no equipment capable of duplicating Loren's synchronization accuracy. Their transmitters lacked the stability, their oscillators drifted, and their scientists lacked the high-speed cathode ray technology needed for microsecond measurement. In every sense, the Americans had built an invisible empire, one that could not be bombed, shelled, or intercepted. A map of pure time, stretching from one horizon to the next. With Loren operational, the range of U.S. bombers expanded overnight. The B-24, once limited by fuel and navigation error, could now fly from the Marianas deep into enemy territory and return precisely to its base. Entire fleets of bombers crossed thousands of miles of storm without scattering. What had once been an act of celestial faith became a science of milliseconds. The Pacific War was entering its final phase. And now, for the first time, it could be fought independent of daylight or weather. The enemy still believed the clouds could hide them. They hadn't yet realized the Americans were navigating inside the clouds themselves. To most of the world, navigation meant a compass and a map. But to the small team of physicists and Coast Guard engineers behind Loren, the Earth was a clock, and the ocean, its face. They worked in unmarked rooms at the Massachusetts Institute of Technology Radiation Laboratory, under the authority of the National Defense Research Committee. Many had already worked on radar, but this project was stranger. Radar sent out a pulse and listened for its echo. Loren, by contrast, compared pulses from stations thousands of miles apart, turning timing into geography. The breakthrough came from a simple realization. Radio waves travel at the speed of light, and if you can measure a difference in arrival time of even a few microseconds, you can measure distance to within hundreds of meters. It was pure physics weaponized. Every Loren transmitter had to be synchronized to atomic precision. Each chain of stations pulsed in mathematically exact intervals, like a symphony of electricity. Any drift, even a millionth of a second, would destroy the grid. To synchronize the network, engineers invented new oscillators, new amplifiers, and the first truly stable master clocks capable of holding time across the Pacific. The entire ocean became a single, invisible instrument, every pulse echoing off the curvature of the Earth. One of the project leads, Commander Lawrence Harding of the Coast Guard, described it simply. "We weren't drawing maps. We were teaching the ocean to speak in numbers." For the men in the air, Loren was both miracle and mystery. Navigators who once charted their paths by sextant and stopwatch now leaned over a flickering green scope, reading pulses that only they could interpret. Inside a B-24 Liberator, the navigation compartment was no larger than a closet. The operator sat between the bomb bay and the radio set, surrounded by paper charts and the quiet hum of vacuum tubes. Through the windowless dark, the Loren receiver glowed faintly, its twin waveforms crawling across a cathode screen. Each pulse pair was a heartbeat of home. The navigator adjusted the dials until the two signals overlapped. That was his fix. He marked it, adjusted for drift, then relayed a correction to the pilot. Even in blind weather, even in darkness, the aircraft remained tethered to those invisible lines. Many crews spoke of it with reverence. They began to trust the machine more than the stars. The navigator's job changed from intuition to interpretation. He was no longer just a guide. He was the reader of a code written across the sky. One veteran recalled, "You couldn't see the ocean, but you knew where you were down to a minute of arc." It was like God had drawn a grid just for us. To the Imperial Japanese Navy, weather had always been a weapon. Their doctrine emphasized surprise under cover of cloud and rain. Their radar was limited, their range-finding optical. Bad weather favored them, grounding American patrols and hiding convoys. That balance vanished in 1944. Suddenly, American bombers appeared through storms that should have grounded them. Japanese interceptors scrambled to empty skies, chasing radar ghosts. Convoys at night were bombed by aircraft that should have been lost. At the Combined Fleet headquarters in Tokyo, staff officers debated the reports. Some blamed improved radar. Others theorized that American navigators were using celestial instruments developed before the war. But nothing explained the timing accuracy. The attacks hit targets even when compasses were unreliable and radio bearings impossible. It wasn't until after the war, when captured B-24 wreckage was examined and fragments of the Loren receiver found, that the mystery unraveled. The Japanese analysts called it an oceanic compass of light. Their post-war report admitted bluntly, it rendered weather and night ineffective as concealment. They had discovered too late that the Americans were fighting a three-dimensional war, not just on land and sea, but across the electromagnetic spectrum. Loren wasn't just a navigation tool, it was a doctrine. It linked aircraft, ships, and submarines into a shared reference frame. A destroyer using Loren to escort a convoy could coordinate precisely with aircraft flying hundreds of miles away, both reading the same invisible grid. For the first time, naval and air operations moved in perfect temporal alignment. Commanders began to plan missions that previously would have been suicidal. Nighttime strikes, over-the-horizon coordination, simultaneous attacks from multiple vectors. Every one of those depended on Loren's silent heartbeat to keep formations coherent. It also changed logistics. Airfields in the Marianas could now send waves of B-29s and B-24s against targets in Japan without visual checkpoints. Refueling routes were plotted across open sea, and search and rescue flights could trace precise bearings to downed crews. It was the first real demonstration of network-centric warfare, long before the term existed. Every aircraft became a node in a lattice of signal and timing. Distance itself had become quantifiable. Before Loren, navigation was an art. After Loren, it became geometry. The ocean ceased to be an unknown void. It turned into a grid of predictable coordinates. A navigator no longer needed to imagine where he was. He could calculate it. The shift was subtle, but profound. It moved warfare from human experience to mathematical certainty. And that certainty carried consequences. If men could find any point on Earth by timing alone, then distance no longer protected anyone. The Pacific, once Japan's greatest moat, had become transparent. In the Air War's final months, that invisibility became unstoppable. No weather, no night, no cloud cover could obscure Japan anymore. The empire's illusion of safety was erased by an invention that didn't explode, didn't burn, and made no sound, only pulses across time. By the spring of 1945, Loren had become more than a navigation aid. It was a living infrastructure stretching across oceans, synchronizing everything from bomber raids to convoy routes. At its peak, more than 70 transmitting stations operated simultaneously, linked through precision clocks and coded coordination schedules. From a command perspective, the effect was revolutionary. The Pacific Theater was no longer a scattered collection of island outposts. It was a connected grid. Headquarters in Guam, Okinawa, or Leyte could plan routes using the same hyperbolic charts that navigators used in flight. Every commander could visualize the same invisible geometry. Where once maps had ended in blue uncertainty labeled unexplored or subject to drift, Loren replaced them with timing curves and intersections. The U.S. Navy called it the lattice of certainty. It allowed coordination between fleets and air wings that had never before shared a single frame of reference. Convoy. Escorts at sea could now vector bombers to distress calls, using only time difference coordinates. Rescue seaplanes reached downed crews hours faster, and when the B-29s of the 20th Air Force began their long-range bombing runs to Japan, they followed corridors of pulse precision that spanned the entire Western Pacific. Even when weather systems tore through the region, the network didn't break. Its radio pulses bent with the Earth, reaching beyond radar range, whispering through static where human sight failed. It was, in effect, the first digital map of the world, built out of timing, not terrain. Loren's power grew exponentially when it merged with another innovation: radar bombing. The H-2X Mickey system, already proving its worth in Europe, allowed bombers to see through cloud using ground reflections. Combined with Loren, the results were staggering. A navigator could locate the target's exact grid position before the radar even resolved it on the scope. In combat, this meant that a B-24 formation could fly through total whiteout, a line on signal, and release bombs within a few hundred meters of the aim point, without visual contact, without sunlight, and often without enemy radar realizing their approach. This synergy blurred the line between navigation and computation. Machines were no longer passive tools. They were interacting systems, one determining location, the other confirming terrain. To the human crews, it felt like the aircraft itself was aware. The fusion of Loren and radar created what modern strategists would later call machine collaboration, a silent dialogue between devices that allowed human operators to act far beyond their own sensory limits. It was an early glimpse of automation's future in warfare. For air crews, the transformation was not only technical, it was psychological. Before Loren, navigation meant constant anxiety. Every minute was a calculation of error margins, every storm a mortal gamble. Crews feared the Pacific's scale more than Japanese flak. They had seen what happened when formations lost cohesion, planes drifting hundreds of miles off course, fuel exhausted, maydays unanswered. Loren changed that forever. Suddenly, even in blindness, they could know. The green scope became a symbol of safety, a quiet, unwavering light that cut through chaos. Crews began to refer to it not as the receiver, but as the guide. When asked after missions what made the difference, pilots didn't mention altitude or speed. They said, "We didn't get lost." That small assurance altered morale as profoundly as any new weapon. The Pacific no longer felt endless. It became measurable, conquered not by bombs, but by information. After the war, Japanese researchers studying captured Allied equipment finally traced the mechanism behind the mystery. They marveled at its simplicity: synchronized transmitters, precision oscillators, timed pulses. They realized it could have been built in Japan had the resources and time existed. But more than the hardware, it was the concept that astonished them. The Japanese mindset in 1945 still saw navigation as a human skill, a blend of intuition, courage, and memory. The Americans had replaced that with trust in systems. In a post-war analysis written by the former head of the Imperial Navy's Technical Bureau, one haunting line stood out: "We trained men to feel the sea. They trained machines to measure it." That sentence captured the technological divide that defined the Pacific, war's end, and the world's future. The network, built to guide bombers across the Pacific, didn't disappear after victory. It became the backbone of global navigation for the next 30 years. Merchant ships, airliners, submarines, All would eventually use Loren chains extending around the world. By the 1960s, it had evolved into Loren C, accurate to a quarter mile, covering 6 continents. It was, in many ways, the grandfather of GPS. The timing algorithms, the hyperbolic geometry, even the philosophy of redundant signal triangulation, all were born in that wartime experiment. When modern engineers designed satellite navigation in the 1970s, they weren't starting from scratch. They were perfecting what those green screens in B-24s had already proven. That location was not a place. It was a calculation, and that revelation began not in peace, but in the most brutal laboratories of war. Perhaps the most profound angle was cultural. For centuries, the ocean symbolized uncertainty, the unknown frontier. Navigation was adventure, but Loren stripped the mystery from the sea. It replaced romance with precision. The Pacific, once poetic, became predictable. That transformation carried forward into every human endeavor that followed. Satellites, automation, drones, and guided missiles, all descendants of the same mathematical faith that defined Loren's success. By the end of the war, the Allies had learned that dominion over the sky didn't require visibility, only synchronization. Invisible, silent, and perfectly measured, Loren marked the moment when navigation ceased to be an act of exploration and became an act of computation. It was not a weapon, yet it changed warfare. It was not alive, yet it pulsed with life's rhythm, steady, continuous, and global. The sky above the Marianas was a cauldron of cloud. Winds whipped at 90 miles per hour. Sheets of rain streaked across the glass of the B-24 Liberators as they lifted into the gray dawn. Ahead of them, 2,000 miles of open ocean, and beyond that, Kyushu, the southern edge of Japan. The men of the 494th Bomb Group didn't expect to see land for 10 hours. They didn't expect to see anything. Typhoon conditions had rolled across the route, erasing the stars and bending compass readings. In 1942, such weather would have canceled the mission entirely. In 1945, they flew anyway, because now they had Loren. Inside the lead bomber, the navigator adjusted the fine dial of his receiver. On the green cathode screen, 2 sine waves crawled slowly toward each other, one from a transmitter on Guam, the other from Saipan. When the peaks overlapped, he marked the time difference, 32.8 microseconds. He checked the chart pinned to the wall. That intersection placed the formation precisely 450 miles northeast of Guam. Right on course, the pilot couldn't see a horizon. The ocean was a void. But the navigator's pencil never hesitated. Every few minutes another fix, another adjustment. The bombers were following an invisible road through chaos. By mid-morning, the turbulence worsened. Ice formed on the wings. Radio static drowned out chatter. The formation scattered slightly, each crew fighting to hold position in the dark soup of cloud. Normally, this was the point of no return. When navigators lost bearings, when aircraft broke apart into isolated fragments across the ocean. But this time, each plane carried its own sense of direction. Each navigator followed the same heartbeat. Loren pulses, faint but unwavering, echoed through their headsets. They knew where they were, and more importantly, they knew where everyone else was too. At 12:47 p.m., the first signal shift appeared on the screens, the telltale sign that they had crossed into Japanese radar range. Without visual confirmation, without a single glimpse of coastline, they were already over enemy territory. Japanese radar stations at Kagoshima scrambled reports. Unidentified formations approaching from the south. Altitude indeterminate, bearings unstable. The storm made radar nearly useless. Commanders assumed it was a false alarm. No sane pilot would attempt a bombing run in weather this severe. But the sky disagreed. At 1:06 p.m., the clouds over southern Kyushu glowed orange from within. Bombs fell through the fog, striking airfields and supply depots near Kanoya with devastating precision. Anti-aircraft batteries fired blindly into the storm, their operators unable to track targets they couldn't see. The sound of engines came and went like thunder. There was no formation to aim at, only echoes. Observers on the ground described it as rain mixed with explosions. To Japanese officers in bunkers, it felt impossible. Aircraft that couldn't possibly navigate had hit them dead on. When the bombers turned for home, they did so calmly, never breaking course. One by one, they reappeared on American radar screens hours later, each within 5 miles of predicted arrival. Not a single plane was lost to navigation error. Loran had passed its first trial by storm. The weapon that wasn't a weapon. In the debriefing tents on Guam, the crews didn't cheer or boast. They simply removed their oxygen masks and wrote in their logs, "Navigation normal." To them, Loran wasn't a miracle anymore. It was just how things worked. But to the analysts reading the strike reports, it was astonishing. Targets destroyed despite zero visibility. No deviations, no lost aircraft, no mid-air collisions. Every bomb group accounted for. One report summarized it coldly. Weather no longer decisive factor in operation planning. That line echoed up the chain of command, from the Air Force to the Navy to Washington. It was more than a victory note. It was a strategic revolution. The Pacific, vast, unpredictable, and deadly, had been neutralized by radio timing. Geography itself had been rewritten. The news of the raid reached Tokyo late that evening. Intelligence officers compared it to prior patterns and found nothing consistent. The attack had arrived through a typhoon, struck within minutes of high tide, and disappeared before interception. Their meteorologists reported that radar performance had been impaired by electrical interference. No one understood what had guided the Americans. One naval staff officer, in frustration, reportedly shouted, "They have trained their machines to know the sea better than we do." He wasn't wrong. Japan's scientists, brilliant but overextended, had spent the war building weapons of force, planes, torpedoes, rockets. The Americans had built weapons of accuracy. Loran didn't kill anyone by itself, but it made every other weapon deadlier by ensuring it always arrived exactly where intended. The end of chance. For the airmen who flew that day, the storm raid became legendary, though never publicized until years later. It proved that even nature could no longer hide the enemy. Typhoons, once the Japanese Empire's greatest ally, had turned traitor. By April, every major U.S. bomber wing in the Pacific was equipped with Loran receivers. They no longer needed moonlight or clear skies. Weather ceased to matter. Night ceased to matter. The bombers came whenever they wished, guided by nothing more than time itself, and in that precision, in those microseconds of synchronization, lay the quiet birth of a new kind of warfare, the kind that would never, again depend on sight. Japan's spring storms had thickened into summer monsoons, layers of cloud stacked over the mainland, blurring every outline into shades of gray. Wind ripped through valleys, lifting salt from the sea and hurling it against coastal cliffs. For centuries, this weather had been Japan's fortress. From the Mongol fleets of the 13th century to the American carrier raids of 1942, the Pacific's violence had always favored the defender. But now, radar stations from Kagoshima to Kure reported something impossible. Bombers were still coming. Not stragglers, not patrols. Hundreds. Their flight paths ignored wind, cloud, and rain as if none of it existed. At 22:41 hours, the first B-24 formations broke across Kyushu, unseen but unmistakable. Japanese air observers on mountain ridges heard the thunder overhead and counted by instinct. 1, 2, 5 squadrons, all maintaining distance through a gale strong enough to ground fighters. No formation lights. No radio chatter, no flares. Yet, when the bombs began to fall, they struck rail junctions, air depots, and dockyards with geometric precision. Down below, the naval staff in Tokyo tried to plot their course, but the weather had shut down their own radar network. Signals bounced uselessly through rain. Officers stared at maps that no longer meant anything. "They cannot see," one commander insisted. "No one can see." And yet, above the clouds, the Americans didn't need to. The grid, in the sky, from the cockpit of a lead bomber, the scene was unreal. Total blindness outside, perfect clarity within. Each navigator bent over his green Loran screen, tracing time difference lines as if drawing the sky itself. Every fix produced another coordinate, another correction. The formation flew as one body, synchronized not by sight but by the pulse of mathematics. At one moment, a navigator announced calmly, "Course verified. Line AB 52 microseconds, line CD 48. To the crew, those words meant certainty. The aircraft was exactly 20 miles south of its target, climbing to 14,000 feet. No guesswork, no drift. When the order came, bomb bay doors open, it was almost ritual. The bombs released in sequence, vanishing into the clouds below. They hit their marks with a precision no human eye could have matched. Below, Japanese factory workers ran into the storm, unable to see where the explosions came from. To them, it was as though the heavens themselves had learned to target. The moment of comprehension. In the following weeks, intercepted Japanese communications revealed confusion bordering on disbelief. Reports described American bombers appearing through storms and attacking without navigation errors. One decoded message from a naval staff officer to the Air Defense Command read, "Enemy aircraft maintain perfect bearings despite meteorological obstruction. Suggest possible new magnetic or stellar equipment. They still imagined a compass, a physical reference." The truth was stranger. The Americans had replaced the concept of direction itself with timing. Captured documents after the war showed Japanese scientists had begun urgent discussions about hyperbolic timing, radio. But the resources didn't exist. The empire was starving, its electrical industry collapsing. Even if they had built the transmitters, they lacked the oscillators to synchronize them. By the time they understood the principle, it was too late. The bombers had already redrawn the map. B-29s. Join the grid. When the B-29 superfortresses took over the strategic bombing campaign in mid-1945, they inherited the full Loran system. Their navigation suites combined the precision of Loran with radar bombing scopes, H-2X, Mickey, and the AN/APQ-13. Together, they formed the most advanced integrated strike system the world had ever seen. From altitudes above 25,000 feet, the B-29s could now bomb through total overcast, guided entirely by signal and waveform. The attacks on Osaka, Kobe, and Tokyo Bay followed Loran corridors drawn months earlier, straight, repeatable, predictable to within seconds. Even when typhoons raged off the coast, operations continued. In July 1945, a full wing of B-29s launched from Tinian during heavy squalls, flew 6 hours through cloud, and struck targets across the Japanese industrial belt with less than 2% deviation. Not one aircraft was lost to navigation error. The Pacific's chaos, once random, unknowable, and deadly, had been quantified. The war in the air had become a function of geometry. The view from the ground in Tokyo, as sirens wailed through rain and thunder, few civilians ever saw the bombers that destroyed their cities. They saw flashes, felt shock waves, and then silence. It was as if the weather itself had turned against them. A Japanese officer later wrote from his bunker diary, "The Americans have found a way to command the storm. Even nature no longer fights for us." To the men who read that after the war, it sounded poetic. But to the engineers who had built Loran, it was literal. The storm wasn't conquered. It was measured, timed, mapped, and made irrelevant. Every pulse across the ocean was a heartbeat of control. Every fix on a navigator's chart was a small act of domination. Not over land, but over uncertainty itself. The end of the weather war. By the time Japan surrendered, the Allies had flown more than 75,000 Loran-guided sorties across the Pacific. The system's reliability rate exceeded 99%. In the final 6 months of the air campaign, there were 0 navigation losses due to weather. When analysts compiled the data, they realized what had happened. The entire concept of weather delay, a constant since the first balloon flight, had been erased. The sky had become predictable. Navigation had become invulnerable. And the empire that had once trusted storms to save it found itself blind inside its own defenses. New era takes shape on the decks of carriers in Tokyo Bay after the surrender. American officers joked that Loran had done its job so well that it was now boring. The grid had made war too easy to navigate. No one got lost anymore. Missions ran like clockwork, but one admiral saw it differently. He stood by the rail, watching the gray horizon flicker with static from unseen transmitters, and said quietly, "We've built something that will outlive all this. The sea will never be the same again." He was right. The invisible network humming beneath the waves would evolve, spread, and one day circle the entire Earth, not as a weapon, but as the foundation of how humanity found its way. It had begun here, with bombers above storms, finding islands and cities by signal instead of sight. That night, the weather stopped being a barrier, and the planet, vast, unpredictable, and wild, became measurable for the first time. When Japan surrendered in August 1945, most of the world celebrated the end of destruction. But for the handful of American scientists, engineers, and Coast Guard technicians who had built Loran, the end of combat didn't mean the end of their work. Their invention, born in secrecy, hidden behind camouflage nets on forgotten islands, had just proven itself in the harshest experiment imaginable, and its success had redefined the limits of what human beings could know about their own position on Earth. The Debriefings. Yithineoan, September 1945. Teams from the U.S. Navy and Army Air Forces compiled the first detailed analysis of Loran's wartime performance. The numbers were staggering. Across the Pacific, the network had guided more than 75,000 missions with an average positional error of less than 1 mile, through conditions that would have grounded any pre-war aircraft. The B-24 and B-29 units that had used it reported 0 weather-related navigation losses during the final 7 months of the war. The entire Pacific Ocean, once the most hostile expanse on Earth, had been tamed by mathematics. The report's conclusion was simple but prophetic. For the first time in history, distance and visibility have ceased to be related. That line, dry and technical, captured the full magnitude of what Loran had done. Humanity had separated where we are from what we can see. The Japanese post-mortem in the ruins of Tokyo, captured scientists and naval officers were shown fragments of Loran receivers recovered from downed American aircraft. They studied the cathode screens, the coils, the precision oscillators, and shook their heads in disbelief. They had spent years developing radar to find ships and planes, but had never conceived of a system to find themselves. Japanese Ministry of Communications eventually published a post-war analysis titled Report on Enemy Navigation by Hyperbolic Radio Lines. Its tone was half awe, half resignation. One passage read, "We underestimated the American ability to convert time into distance. Our defenses were prepared for visibility, not for precision beyond the senses." The phrase, "beyond the senses," appeared repeatedly. It marked the moment the imperial war machine realized that technological mastery no longer depended on strength or speed, but on synchronization. Back in the United States, the men who had created Loran met quietly at the MIT Radiation Laboratory in late 1945 to discuss peacetime uses. Some were relieved that their system had saved so many lives by preventing lost aircraft. Others were uneasy. They had built the world's first global positioning grid, and it had been used to guide destruction. Commander Lawrence Harding, who had overseen the Pacific Loran expansion, wrote in his notebook, "We have made the Earth measurable. We have also made it smaller." That sentence became a kind of unofficial epitaph for the project. Because once humanity could measure itself anywhere, the idea of isolation, of being unreachable or unfindable, ceased to exist. From war tool to peace network, as demobilization began, most secret technologies were dismantled or sealed away. But not Loran. Instead, it expanded. The same stations that had guided bombers now guided merchant convoys, medical transports, and supply fleets ferrying troops home from Asia. The Pacific, which had consumed so many lives, was now mapped by the very same pulses that had once guided bombs. By 1946, the U.S. Coast Guard was operating a permanent Loran chain across the Pacific, Atlantic, and Arctic. Ships carrying humanitarian cargo into shattered ports, Tokyo, Manila, Hong Kong, sailed safely through fog and typhoon alike, their navigators following the same hyperbolic lines once used for war. In a way, the network had already transformed into something peaceful, a grid of trust connecting continents instead of destroying them. In Washington, few politicians understood Loran's significance. It didn't explode or flash across headlines like the atomic bomb. It was quiet, invisible, methodical, precise, yet historians would later argue that it was one of the three inventions that made global civilization possible after 1945. Without it, there could be no long-range commercial flight, no transoceanic shipping safety, and no scientific exploration of the poles. The secret network that had guided bombers to Tokyo now guided fishing boats through fog off Alaska, icebreakers in the Arctic, and aircraft across the North Atlantic. It was the unacknowledged infrastructure of a shrinking planet. In post-war interviews, one engineer put it this way: it was the first time humanity could locate itself without asking the sky. The irony of precision. In Tokyo's reconstructed universities, Japanese scientists studied Loran technology for years afterward. They saw in it not defeat but instruction. Many of them, men who had once built air defense radar, went on to develop Japan's early civil aviation navigation systems. The country that had been blind beneath storms became one of the first to rely on electronic navigation for peace. Meanwhile, in America, Loran's engineers were already looking ahead. They saw the next frontier not in radio waves bouncing off the atmosphere, but in signals from orbit. The mathematics of hyperbolic timing, perfected in 1945, became the seed for the satellite navigation systems that would follow decades later. Every GPS fix, every satellite triangulation, every automated drone flight still follows the same principle that guided a B-24 through a typhoon. Find yourself through time, not through sight. The end of mystery in the 19th century. Sailors had called the Pacific the blind ocean. No one could cross it without faith in the stars. In the 20th, that faith had been replaced by numbers. And by 1945, those numbers had proven more powerful than any weapon or empire. When the last wartime Loran stations were shut down decades later, their operators held a small ceremony. They lowered the antenna masts and switched off the transmitters one by one. The silence that followed was almost reverent. One old radio man, who had first manned a Pacific outpost in 1944, summed it up quietly. When we turned it off, it felt like the Earth was breathing on its own again. He wasn't wrong. For a single decade, humanity had built a nervous system across the planet, a web of pulses that linked every horizon. And when the war ended, that web didn't vanish. It simply became invisible. In the peace that followed, the Loran towers kept transmitting. The war was over, yet their steady pulses continued to sweep across the oceans, a quiet rhythm of order amid the ruins. The same signals that had guided bombers through storms now guided hospital ships, transports, and cargo convoys bringing food and supplies to a shattered Asia. The U.S. Navy and Coast Guard quickly realized that Loran's usefulness extended far beyond warfare. The Pacific, once a battlefield, was now a reconstruction zone. Merchant fleets relied on Loran charts to reach devastated ports in Japan, Korea, and the Philippines. Search and rescue aircraft used the same invisible corridors that had once carried bombers. Mariners who had never heard the word hyperbolic navigation found themselves steering by it. In post-war planning conferences, Allied commanders described the system as the compass of peace. For the first time, global logistics could operate with mathematical precision. The same principle that had erased fog and darkness in war now erased uncertainty in trade and exploration. The line between military innovation and civil progress had dissolved. At the scientific level, LORAN became the foundation of a new age of navigation. The system's engineers, many from MIT's radiation laboratory, returned home to continue their research, refining the technology for civilian use. The resulting network, LORAN-A, blanketed the Atlantic and Pacific by the early 1950s. It provided navigational accuracy to within half a mile across thousands of nautical miles, a marvel unmatched until satellites would one day circle the Earth. As nations rebuilt, other powers took note. Britain adapted its wartime G system for civilian aircraft, while the Soviet Union developed a counterpart for Arctic routes. Yet none matched the scale or stability of the American LORAN grid. By the time the Cold War began, the invisible map drawn during World War II had expanded into a permanent architecture of global positioning. Every merchant ship, survey aircraft, and naval submarine operated within its rhythm. For Japan, the irony was deep. In 1946, under Allied occupation, Japanese scientists were invited to study the technology that had defeated them. Many came from the same universities whose wartime laboratories had tried in vain to decode it. They found not mystical power, but disciplined precision, oscillators, pulse generators, and mathematical charts. One engineer, seeing a working LORAN receiver for the first time, reportedly whispered, "We lost not to force, but to time." Throughout the 1950s and 1960s, the old wartime towers were rebuilt, automated, and incorporated into a new global network. Some stood on the same windswept islands where servicemen had once maintained them by hand. Their antennas rose again, now tended by technicians who guided peacetime traffic instead of bombers. Ships crossing the Pacific plotted their courses by LORAN lines, unaware that those lines had once carried the ghosts of war. By the time satellite navigation emerged in the late 20th century, the logic behind it was already 40 years old. GPS would use the same principle that LORAN had proven under fire, measuring distance through synchronized time signals. Every satellite orbiting the Earth carried, in a sense, the legacy of those first wartime pulses that connected the islands of the Pacific. Many of the original LORAN towers have since been dismantled. The last stations in the United States went silent in the early 21st century. On some islands, the bases remain: rusted generators, cracked concrete, and the skeletons of steel masts facing the wind. To the casual visitor, they are relics of forgotten communication outposts. But to those who know their story, they mark the birthplaces of invisible navigation, the first points on a global grid that still shapes every flight, every ship, every phone signal tracing its location on Earth. In museums and archives, a few of the wartime receivers remain, their screens faintly glowing when powered on, echoes of a time when green waves on glass decided the fate of fleets. What began as a desperate wartime experiment had become a permanent language of position. LORAN's legacy was not only victory, but the human conquest of uncertainty. The Pacific, once an ocean of chance, had become an ocean of coordinates. And in that transformation lay one of the quietest revolutions in human history. In the long silence that followed 1945, the world began to understand that victory had not only been won by courage or firepower, but by synchronization. The P-61s, the B-29s, the fleets that crossed oceans, all of them had depended on a rhythm too small for human senses to feel. A difference of microseconds had redrawn the map of war. The Japanese staff who once watched their radar screens in confusion had witnessed something profound. The moment when visibility ceased to matter. The old order of warfare, dictated by weather, daylight, and horizon, had been quietly replaced by mathematics. In the storm's heart, a new kind of certainty was born. LORAN was more than a navigation system. It was the first global language of timing, a proof that by measuring the difference between two invisible signals, humanity could locate itself anywhere on Earth. Every coordinate, every path traced since then, from Cold War bombers to modern GPS receivers, began with those flickering pulses sent from lonely towers over the Pacific. The beauty of the system lay in its humility. It had no roar, no flash, no emblem of power. Just the soft click of transmitters, the hum of vacuum tubes, the green whisper of a waveform on glass. Its strength was patience, the quiet insistence that time itself could be trusted more than sight. In that sense, Lauren's true legacy was not in destruction, but in discipline. It turned chaos into structure, storms into geometry, oceans into grids. It showed that even in humanity's darkest hours, precision could serve understanding, that through the measure of seconds, the world could be held steady. Today, satellites trace the same invisible logic across the heavens, their signals still echoing the lessons of that war, that mastery of time is mastery of space, and that even in the deepest storm, there is a line that leads home. The Japanese staff who once stared into clouded skies could not have known it, but what they saw was the beginning of a new age, an age where the Earth would never again be truly lost in the dark.